Hey everyone, welcome back to another CIE A Level Physics past paper video. Today we're going to talk about paper 4, variant 4.2 from the February-March 2024 series. But before we get into the paper, let us show you some resources that we developed and which are going to be immensely helpful for you. So these resources, this great booster pack is available on the Patreon, and the link is given below in the video and in the description also. So what it contains are few documents and few resources, such as, for example, AS definitions and formulae. So as you can see, it contains definitions. This is a list of reasonable estimates, and it goes all until the particle physics. Then we have frequently examined questions for paper 2, structure theory questions. Some questions we know already are frequently examined. Important derivations that are frequently tested in exams. Paper 1, paper 2. A2, definitions and formulae, similar to AS1. Key terms, key formulae, whether they are vector or a scalar, important concepts. Then we have important derivations. Obviously there are some derivations that come up again and again. So for example, this comes up again and again in different forms. So it would be good if you read through that. Graphs are very important. We know that most of the students get stuck between the field and the potential graphs for gravitational fields and electric fields, so we have them here for you along with a mathematical description, so you can study them and see how they look like. Then we have the most important one, which is A2, frequently examined questions for paper 4, and as you can see, we have structured it very differently. On the left side you have syllabus contents, then you have questions and their respective answers, and the years listed on the right. Now there are going to be some questions where you will see a lot of years written on the right hand side. That just simply means that they are the questions that are very frequently examined. Now if you don't see any year with it, that does not mean that question is not answered. It just means that I started writing the years very recently, so I haven't caught up to that. But these questions are from the past papers anyway. And last but not the least, for paper 5, experiment planning question. This is a checklist that's in line with the marking scheme and the syllabus requirements. And some solved questions also, how you can actually use them. Right. And once again, they're all available on Patreon. You should check this out. And let's get into the paper. Okay, so question number 1. Explain why the gravitational potential near to a point mass is negative. Now, there are 2 points to this, and one of the points you can rephrase it differently. So basically, for example, if this is the source of the field and we want to move either a mass from infinity to this point, for example, some point away, like some point from the source of or the mass body. So we want to either move this point to the infinity or from the infinity to that point. So either way, there's a difference, because this way, this direction is positive displacement and this is the negative displacement. Now, why does it matter? Because if you want to go in the positive displacement direction, force is negative, because you're doing work against gravitational field. So force is this way. So although you are raising the potential energy by working against gravity, but at infinity the potential is 0. Okay, so you are doing work against gravity to raise the potential energy. However, potential at 0 is negative. Potential at infinity is 0. So basically, like all the previous work that you have done is still negative, because you're working against gravity. Similarly, if you are moving from infinity to this, so the same reason, basically the work is done by the field to move from infinity, which is at 0, to a point closer to the mass. And since you're basically work is done by it, there's going to be a loss in gravitational potential energy. So it's going to result in a negative potential. So the magnitude part will definitely increase, but it's going in the other direction. So that's why. So 2 points. You can write it either way. So work is done by attractive gravitational field to bring a mass from infinity, where potential is 0, to a point closer to another mass, resulting in negative potential. Now you could rephrase that in the work done against gravity, in moving a mass away from another mass to infinity, raising the potential energy to 0. You can also say it like that also. So how would you phrase that? Let's write over here that the work is done against gravitational field to move a mass away from another mass raising its potential move a mass away from another mass, raising its potential to a point closer to infinity, or to infinity, to actually we should rephrase that. Work is done against gravitational field to move a mass away from another mass to infinity, raising its potential to 0 at infinity. So these 2 points combined together. Right, okay. Part B. Planet may be assumed to be a uniform sphere. It has a gravitational potential phi at a distance r from the center of the planet. Okay, the variation with 1 over r of phi is shown in figure 1.1. Okay. Show that the mass of the planet is 8.8 10 raised to the power 25 kg. Okay, so this is phi and 1 over r. So we know the relationship between phi and 1 over r, that is gm over r negative. So this means that the minus gm is our gradient and 1 over r is our basically x. So this is y, x, and minus g. So your gradient, which is negative already, is minus gm. So m is going to be your gradient minus g. So we need the values. So let's find out any point. So one point can be 0, 0. We need another point. So negative, negative, negative. Okay, alright. I think I see one point over here. This point over here. This is 3. And we need to see how much this is. So 0.4 units covered in 10 grids or 10 minor graduations or like minor boxes over here. That means 0.01 in every mark. So 0.04, sorry, 0.04. So we have 1, 2, 3, 4. So 4 times by 0.04 plus 1.6, that is 1.76, but negative, right? So you have negative 1.76, 10 raised to power 8, minus 0. Then this is 3, 10 raised to power minus 8. Minus 0. Yeah, divided by G, which is 6.67, 10 raised to power minus 11. Okay, so minus G. The minus minus we can like forget about that. So 1.76 divided by 3 divided by 6.67 times by 10 raised to power 8 plus 8 plus 11. Right. So basically, as you can see, this is coming out to be 8.795 10 raised to power 25, which can be rounded to 8.8 10 raised to power 25 kgs. Alright. The period of rotation of the planet is 0.72 Earth days. A satellite in orbit around the planet remains above the same point on the surface of the planet. That means it's a geostationary satellite. Not geostationary, this is geosynchronous. Use the mass of the planet in B1 to determine the radius r of the orbit of the satellite. So we know the relationship. So that is going to be, we have done this many times, so this is going to be r cubed over, r cubed is equal to 4 pi squared gmt squared. So we need the r. So r cubed is equal to 4 pi squared. Sorry, I wrote it the other way around. This is gm over 4 pi squared. G is 6.67, 10 raised to power minus 11, times by 8.8, 10 raised to power 25, 4 pi squared, times by, time needs to be in seconds, so 0.72 of 24 hours, 3600 seconds in an hour squared. So we need 6.6, wait. Let's do the cube root thing. So 6.67 times by 8.8 divided by 4 pi squared times by 10 raised to power minus 11 plus 25 times by 0.72, 24 times by 3600. So we are getting r to be 8.3 10 raised to power 7 meters. Okay. The speed of the satellite in B2 is 8400 meters per second. The mass of the satellite is 1200 kg. Determine the additional energy required to move the satellite from its orbit to infinity. Now, although this is clear that there is a gain in potential energy from the orbit to infinity, so like there's a gain in EP is rising, and going from over here the EK is decreasing. So EK is decreasing to 0 over here. EP is also 0, but it's for potential is actually growing to 0 over here. So this is going to be GMM over R instead, the change in potential over here. So basically the change in potential energy plus change in kinetic energy will be our work done. So the work done is gain in EP plus change in EP, let's say, plus change in kinetic energy. So that is your GMM over R plus change in EK, that is going to be half M V squared minus U squared. Now V is 0 over here. Right. Before I solve this, if you have any problem understanding how this is happening, you can try to derive this using first principles also. So for example, you have a point R over here, this is the source, this is the infinity, and you have a point mass. Let's say this is the driving force, this is the gravitational force, and we want to move, let's say this is point R, sorry, my bad. So we want to move this to infinity, right? So the work done by dg is equal to, d minus force of gravity is equal to ma. So since like the gravitational force is not constant across the way, so we can't just simply multiply it by the displacement s. So we need to integrate this. So integration d ds minus integral f ds is equal to net change in ma. So again, you see the acceleration will also not be constant. So when we integrate acceleration with respect to displacement, if those of you who can do that, remember A is basically, although dv over dt, but if you use the chain rule, dv over dx and dx over dt over dx, or you can use the chain rule over here. Actually that would have been much simpler. Dx and dx over dt, dx over dt is v itself, so this is v dv over dt, sorry, my bad, what am I doing? dx, yes. So when you integrate this with respect to x or s, whatever we want to call it, we would actually just get a net change in this thing. Now why I kept it in integral? Because force is not constant across the space over here. Now when we take force, because this force, although it's negative, but when we take it on the other side, it becomes negative. So as long as it's on the left hand side, it represents the work done against gravity. This is, let's say, from R to infinity, R to infinity, R to infinity. But when it goes on the other side, we can just simply take it as GMM over, let's say, R or S, sorry, ds. And we know what we will get over here. So this represents the net work required. This is the let's integrate this over here. So you have GMM over let's call it s raised to power minus 2 ds from R to infinity. You get minus GMM over s from R to infinity. So at infinity, s, like s, when s is infinity, this function would be 0, minus GMM over R. So basically this would be positive. So GMM over R, and this thing V is already 0, so this would become minus half mu squared. So that is what we have over here. So we will simplify this too. This is 0. So you have GM. Wait, sorry, did we have GM over here? No, never mind. So 6.67 10 raised to the power minus 11. Mass is 8.8 10 raised to the power 25. Mass of the satellite is 1200 kg. Radius of the orbit is 8.3 10 raised to the power 7 minus half m v squared. So that's what we need. So 6.67 times by 8.8 times by 1200 divided by 8.3 times by 10 raised to the power minus 11 plus 25 minus 7 minus 600 times by 8400 squared. So this is going to be 4.3 10 raised to the power 10 joules. Right, so that's it. And that's it for the first question. Let's move on to the next one. Question number 2. By referring to both kinetic energy and potential energy, explain what is meant by the internal energy of an ideal gas. So basically, the internal energy of the gas is the total microscopic sum of or the total sum of the microscopic kinetic energy and potential energies of the particles. And if you have any problem, we have this in the frequently examined questions also. So let's see that. Okay, so let's see this. The internal energy of an ideal gas is the sum of random kinetic energies of its molecules plus the total potential energy. Since there are no intermolecular forces in an ideal gas, potential energy is 0, so internal energy consists of only of kinetic energy. So the internal energy of an ideal gas represents, is the sum of kinetic energy of the particles due to their random motion and the potential energies of particles and the potential energies associated with intermolecular forces. The potential energies is 0 since there are no intermolecular forces in ideal gas. Okay, alright, let's see the B part. A fixed mass of an ideal gas at a temperature of 20 centigrade is sealed in a cylinder by a piston shown in figure 2.1. The initial volume of the gas is given as 1.2 10 raised to the power minus 4. The thermal energy supplied to the gas and its volume increases by this. The piston is freely moving, so the gas is always at atmospheric pressure, so the pressure is constant. Atmospheric pressure is this. Calculate the work done by the gas. So if the pressure is constant, so the work done by the gas would be P delta V. So the pressure is 1.01 10 raised to the power 5, and change in volume is basically 5.2. This is increases by, so this is the change in volume. So 1.01 times by 5.2, because 10 raised to the power 5, 10 raised to the power minus 5 will cancel each other out. So 5.252, so basically 5.3 joules. Actually, we should keep it to 3 significant figures because all of them are in 3 significant figures. So 25 would be a better answer. Okay, calculate the final thermodynamic temperature of the gas. This is an ideal gas, right? Right, this is an ideal gas. So the PV over T is going to be constant. So PV over T is going to be equal to P2V2 T2. Pressure is the same, so basically the T2 over T1 is equal to V2 over V1, right? V2 over V1, right? Okay, so we have T2, V2 is the, remember this is not the change, so initial 1.2, 10 raised to the power 1.24, 10 raised to the power minus 4, and then plus 5, 10 raised to the power minus 5, what was 5.2, sorry, divided by initial volume was 1.24, 10 raised to the power minus 4. And temperature 1 was 20 degrees Celsius, so 20 plus 273.15. Okay, that's what we need over here. So we have 1.24 times by 10 raised to the power minus 4 plus 5.2 times 10 raised to the power minus 5 divided by 1.24 times by 10 raised to the power minus 4, and this is all times by 293.15. So this is 416.083 basically. 08 was fine also, so 08, so 416 kelvins. Alright, the mass of the gas is 16 grams. For this expansion there is a net transfer of 960 joules of thermal energy to the gas. Calculate the specific heat capacity of the gas at this pressure. Okay, so we have C is equal to the thermal energy transfer and M times by change in temperature. So 960 divided by mass is 16 grams, which we needed in kilograms. Change in temperature is, we can say, 416.08 minus 293.15. Basically we can do 416 minus 273 also. Either way that would be fine also. So 416 minus 273, 143. No, sorry, 293. 123. So basically the unit change is 123. Right, okay. So 960 divided by 16 times by 1000 divided by 123 is this value. 487.8, which is 488 joules per kilogram per Kelvin. The gas in B is allowed to return to its starting temperature. The piston is now fixed in position. Okay, and that means the volume is not allowed to move or change. The thermal energy is supplied to increase the temperature to the same final temperature in B. Use the first law of thermodynamics to suggest and explain how the specific heat capacity for the gas for this situation compares with the value in B3. So let's look at this mathematically. So we have the first law of thermodynamics is basically this. So no same final temperature. Basically the wait a second, as in B. Okay, so if the volume, so first off, they fixed the position, so volume is not changing. So that means this is going to be 0. And since this is an ideal gas, the internal energy change would be is directly proportional to the change in kinetic energy, right? So, okay. Now the change in volume is 0, so no work done by the gas or on the gas. However, it's still supplied with the same. No, we don't know what's the same temperature. Is it the same temperature? No, same energy. Thermal energy supplied to increase the temperature to the same final temperature at that. So the change. Okay, so the net change in internal energy would be the same because we are going from the same 20 degrees Celsius to 123. No. Sorry, no. To 416 minus 273, that is 143. Okay, 143 degrees Celsius. So the net change in kinetic energy is the same. Net change in internal energy would be the same. However, what's changing is the net change in that. So this is your MC delta T. So this is the same, this is the same. So what's changing, however, is this part. This is not there anymore. So when this was present, the work, the specific heat capacity was first impacted. So now we can actually test the values also. So basically we have 5.25 over here. Oh, sorry, we had 5.25 over here. Now it's 0. Okay, so previously the 5.25 was added in delta Q. Now it's not added. So the delta Q is lower this time. So delta Q is lower this time. The mass is constant, change in temperature is constant, so therefore C is lower. So that's what we just need to write. So no work is done by the gas since no volume changes. During this operation. Also, the net change in internal energy would be the same as the change in temperature, as the net change in temperature is same as before. Therefore, the thermal energy required, the heat required, the thermal energy required would be less, meaning therefore so the heat capacity, so the specific heat capacity would be lower as well. Okay, so that's it for this question. Let's move on to the next one. Okay, so question number 3. A small object of mass 24 grams rests on a platform. The platform is attached to an oscillator as shown in figure 3.1. The oscillator moves the platform up and down. The total energy of the oscillations of the object is 2.2 10 raised to the power minus 4. In one oscillation, the object travels a total distance of 14 millimeters. So total distance, this is not the amplitude. So we need the angular frequency of oscillations. Okay. Right, okay. So you see the total distance, basically, it is basically this. So 1, 2, 3, 4. So basically, half of this would be an amplitude. And, no, sorry, quarter of that would be an amplitude. So, we know the total energy of a system in simple harmonic motion. The formula is half v squared, and v maximum speed, maximum kinetic energy is omega x naught squared. The total energy is given as 2.2 10 raised to the power minus 4. This is 1/2. Mass of the object is given 24 grams. Okay, so 24 10 raised to the power minus 3. Oh, we need to figure out omega, and the x naught is quarter of this times by 10 raised to the power minus 3 whole squared. So we need to solve for omega, but let's clean out this on the right hand side. 24 divided by 2 is 12, 10 raised to the power minus 3 omega. 14 divided by 4, it's 7/2, and 7/2 squared is 49 over 4, and this would be 10 raised to the power minus 6. So omega would be 4 times by 2.2 10 raised to the power minus 4 divided by 12 10 raised to the power minus 9. 49 also, sorry. Right. And yeah, okay. Alright, let's solve this. So 4 times by 2.2 divided by 12 divided by 49 times by 10 raised to the power minus 4 plus 9. Oh, sorry, this is omega squared, by the way. So this is the 1496. Let's say 6. We need the square root of this would be 38.6. So therefore omega would be 39. Two significant figures. Frequency of the oscillator is fixed. The amplitude of the oscillations is gradually increased. Calculate the maximum amplitude of the oscillations so that the object does not lose contact with the platform. So that will only happen if we maintain contact with the platform. That means there is a normal reaction force always. Okay, so there is a weight mg. So remember the restorative force, the force that is responsible for the simple harmonic motion acceleration, when it's going like upwards, when the motion is upwards, it will be directed downwards. Acceleration would be downwards. And if the displacement is downwards, the acceleration would be upwards. So acceleration is always in the opposite direction. So we need to find out the maximum amplitude of the oscillations so that the object does not lose contact with the platform. So we need maximum displacement. Let's see how we can actually do that. So if we have the force over here, we can find out the maximum acceleration also. So mg minus r equals to ma. So the point where it loses contact is when r becomes equal to 0. So that means acceleration g. Right, so weightlessness basically. So that would be the maximum acceleration that we need. So that would be the maximum acceleration. So if we have the maximum acceleration, we can figure out the maximum amplitude also. So omega is 39, so x naught would be 39 over, acceleration we found out to be 9.81 divided by 39 squared. Okay, so at the point of contact, the acceleration is going to increase as we're moving upwards. So this is positive x, so the deceleration you can say, or the acceleration will increase. So at the highest point, it will start to move back. So we don't want that to happen. We need r to always be greater than 0. But to do that, we need to figure out when it becomes 0. So when it becomes 0, acceleration would be g. So that means it returns back, it starts to return back with acceleration equals to g. That's when it will happen. So going back, oh, this is already squared that we have. So this is 9.81 divided by answer. So this is the 0.0065. Yeah, so basically 0.0065 meters. Right, okay, moving on. The amplitude of the oscillations is increased so that it's greater than the value in B1. Okay, alright. State and explain the position in oscillation where the object first loses the contact with the platform. So basically all what we explained over here, we need to write it in words, right? So the object will lose contact with platform when the contact force, or the normal contact reaction force, becomes 0. This will happen when acceleration downwards becomes equal to acceleration due to free fall and will occur and will lose contact at the highest point of its oscillation. Okay, so it will go like this, and then it will sort of, like you can say, it will jump up when the platform starts to come back with acceleration equals to g. Oh, sorry, no. Since it is like going upwards, the downward acceleration would be like this. Yeah. Okay. Okay. This is question number 3. Let's move on to question number 4. Question number 4. 3 capacitors are connected as shown in figure 4.1. Determine the total capacitance in microfarads of the network of the 3 capacitors. Okay, so remember, when we have in parallel, we just simply add their capacitances, and when we have in series, we add them like we add parallel resistors. So we have 1 over CEF equals to 1 over 45 micro plus 1 over 30. So this becomes, you can say, 30 plus 45 over 45 times by 30. So you have 75 divided by 45 times by 30, that is 1350. So therefore the CEF would be 1350 divided by 75. So that is 18 microfarad. Okay. The capacitor of capacitance 45 microfarad is connected to a variable power supply initially set at 8 volts. The output of the power supply increases so that the potential difference across the capacitor increases to 9.6 volts. Calculate the increase in energy stored in the capacitor. So, we know the energy, potential energy stored in a capacitor is half CV squared. So before, actually we can just simply straight away find out the E. So half C remains to be 45 micro, but what's changing is the potential difference. So 9.6 squared minus 8 squared. So we have 0.5 times by 45 times by 10 raised to power minus 6 times by 9.6 squared minus 64, which is 8 squared. So this is this. Let's convert it into standard form. 1, 2, 3, 4. Minus 4 joules. Okay. A sinusoidal AC power supply is connected to the input of a bridge rectifier. The output of the rectifier is connected to a load resistor. Complete the circuit in figure 4.2 by adding a capacitor to smooth the PD across the load resistor. So it's always in parallel with the load resistor. Oh no, sorry. Oh, sorry. I meant capacitor. Okay. The variation with time t of the potential difference of a smoothed output is shown in figure 4.3. Determine the time constant in ms of the smoothing circuit. Now, basically, we have the relationship V equals to V naught E raised to power minus T over time constant, which is RC. So we need the time constant, so we basically need two values that are starting, and we need the time difference between them also. So let's start with 5 and let's end it over here. Okay, so this is 11, 12, 13, and this is 5. Okay, so it's starting with 5, 4, the distance, like the time difference between them, is 8 milliseconds, and the voltage drop is, let's see, 3.2. So this is 3.2. So the voltage drop would be 0.8. Okay. So we have V over V naught equals to E raised to the power minus T over tau. So minus T over tau would be ln V over V naught, which would simplify to tau minus T, which is the time, divided by ln V over that. Right? Okay. So this would be minus 8 milliseconds divided by ln 3.2 divided by 4. Right. Okay. So minus 8 times by 10 raised to the power minus 3 divided by ln 3.2 divided by 4, so which is this thing. This is coming out in so if we had used this in milliseconds, we would have gotten the answer in milliseconds also. So for example, if we reduce this, because e raised to the power that is just the ratio between the voltages, so this would get us let's go back, times by 10 raised to the power minus 3, so times by 10 raised to the power minus 3, this is 0.0358 seconds. So 1, 2, 3, it would be 35.8 milliseconds. So 36 milliseconds. Right, okay. A sinusoidal AC power supply has a maximum power of 16 watt. State the value of the mean power of the output when the power supply is full wave rectified. Full wave rectified. So when it is full wave rectified, it will have the same mean power supply as it has on a normal case, on a normal like the sinusoidal case. So mean power basically is maximum power divided by 2. So if it is that, mean power would be 8. Half wave rectified would further reduce by half, because half the time the signal is not available, so that would be 4 basically. So that's just that, and that's it for this question. Let's move on to the next one. Question number 5. An object travels in a circle at constant speed. State the names of two quantities that vary during the motion of the object. Okay, so this is an interesting question, and we have this in these frequently examined questions. Let us show you. Right, look at this. So velocity is changing, angular displacement is changing, momentum is changing, centripetal acceleration, and the resulting force is changing. Everything other than the speed is changing. So you can say velocity, you can say acceleration, you can say momentum, linear momentum, because velocity is changing, so linear momentum is also changing. Yeah, that's it. Similarly, the acceleration is changing, so the centripetal force would also be changing. Similarly, the angular displacement would also be changing. Right, okay. A charged particle of mass m and charge q enters a region of uniform magnetic field perpendicular to the field lines. The magnetic flux density is B. The particle travels in a circle with a period t and radius r. Okay, by considering the magnetic force acting on a particle, show that B is equal to 2 pi m over qt. Right, okay. So we know that the magnetic force is BVQ, and sine theta is already like sine 90 because it's perpendicular to that. That is equal to centripetal force. Sorry, mv squared over r, but this time we need t and r in the mix. So we will use the mr omega squared, where omega is 2 pi over t. So, we don't have v over here now. Okay, alright. Charge q, mass m, b is this, but we do not know anything about. Right, okay. I think we can figure this out also. Okay, so first off, b is going to be m r 2 pi 4 pi squared over t squared divided by vq. So v is r omega also. Yeah, because v is r omega. That's how basically we could have actually cancelled out. So let's see. B is equal to r omega q equals to m r omega squared. So r gets cancelled, omega gets cancelled. So B would be m over q times by 2 pi over t. Right. So 2 pi m over qt. Right, okay. The particle is an alpha particle. The period of the circular motion is 25 microseconds. Calculate B. Right, okay. So mass of an alpha particle is 4u, where u is 1.66 10 raised to the power minus 27. I think we can check the value. We can use this one. So for u, 1.66 10 raised to the power minus 27, and charge is 2e, 2 times by 1.6 10 raised to the power minus 19 coulombs. Okay, so B would be 2 pi times by 4 times by 1.66 10 raised to the power minus 27 divided by 2 times by 1.6 10 raised to the power minus 19 and microseconds, so 2.5 10 raised to the power minus 6 times by 4 times by 1.66 divided by 2 divided by 1.6, 2.5 times by minus 27 plus 19 plus 6, we get this value, so 0.052 Tesla. Okay, the second alpha particle is in the same uniform field. It travels at a circle of radius 2r. Then explain how the periods of the motion of the two particles compare. So normally, like if you remember the orbiting satellite, we would have said that the period would have increased with this relationship. However, if we notice the relationship we derived over here, which is, if I rewrite this over here, this is this thing, or the time period. So basically, if you rearrange, this is 2 pi m over b cubed. So it's in the same uniform field, so that means b is constant, charge is the same, mass is the same, 2 pi is a constant, so that means t is also the same. So we will say that the period of the second alpha particle is the same as the first one, because the period does not depend on radius. Circle. Right. Okay. Moving on. The speed of the alpha particle in B2 is 1.1 10 raised to the power minus 6. An electric field is also applied that this particle now moves with constant velocity. Constant velocity means that speed in constant speed and in a constant direction. Okay. Use your answer in B2 to calculate the electric field strength. So basically, if it's moving with a constant velocity, that would mean that the force due to magnetic field is balanced by force due to electric field. So either it's now continues to move perpendicular to these two forces, which is most likely going to be the case, and otherwise it could be still moving parallel to these forces also, because the acceleration previously was parallel to this. However, remember that previously the magnetic force was, which is the centripetal force, was moving perpendicular to the speed. So if we supply now the electric force also, it will continue moving in this direction, constant velocity. So that's basically that. So force due to magnetic field will be equal to electric field. So B V Q equals to Q E. So Q will get cancelled. So E would be equal to BV. So B was, we found it to be 0.052 times by speed 1.1 10 raised to the power 6. So this value times by 1.1 10 raised to the power 6. So we get 57,365. So basically 57,000. And it's force over charge. So basically Newton per coulomb also. It could be V over D, volts per meter. So Newton per coulomb. And that's it for this question. Let's move on to the next one. Question number 6. A small coil C has 64 turns and a cross-sectional area 0.71 centimeters squared. The coil is placed inside a solenoid as shown in figure 6.1. Okay. Right. The center of coil C is on the central axis of the solenoid. There is a constant current in the solenoid. Coil C is moved through the solenoid from position X to Y. On figure, sketch a line to show the variation of the magnetic flux linkage in coil C with the position as it moves from X to Y. So remember, the field inside the solenoid will be uniform. So flux linkage would also be uniform. So somewhat like this, straight horizontal line. Okay, explain the shape of your line in A2. So the magnetic field, you can say flux also, is uniform inside the solenoid. Actually, the better word should be magnetic flux density. Field strength, basically. Flux density is uniform inside the solenoid, and flux linkage is proportional to B, and actually, equal to BAN. All of those are same. And it is, magnetic flux linkage is proportional to flux density as cross-sectional area and number of turns is constant. Hence, constant horizontal line. At a non-zero value. Right, okay. Coil C is now held stationary at point X. The current in the solenoid varies so that the magnetic flux density B at X varies from time 0 to time 4t as shown. Okay. Calculate the maximum flux linkage in coil C. Okay. So this is equal to BAN. So that means we already said that this is proportional to B. So wherever the maximum flux density is, will be the maximum flux linkage. So that would be 0.08 cross-sectional area and number of turns were given over here. 0.71 and 64. So 0.71 10 raised to the power minus 4 meters squared and 64 turns. So 0.08 times by 0.71 times by 64 times by 10 raised to the power minus 4. This is 1, 2, 3, 4. Minus 4 Weber. Okay. On figure 6.4, sketch a line to show the induced electromotive force EMF in the coil C from time t is equal to 0 to time t 40. So remember, the EMF induced is proportional to the rate of change of flux. Actually, it is equal to that, And technically it is the negative, however, the negative part is not exactly forced upon us, but the sign change will be forced upon us. That means that is mandatory. So over here the flux density is not changing, so B is not changing. So as you can see, magnetic flux linkage is proportional to B, so any change in magnetic flux linkage will also be directly related to change in flux density. So flux density is constant from 0 to t, so induced EMF would be 0. Okay. Then we have an increasing uniformly increasing B, which means that uniform non-zero value of induced EMF, and we need to see the gradient also. So rise over run is basically 1. So gradient, the change in B over change in T is 1, and over here in this part, rise 4 units drop, 4 units over there. So basically change in B over change in time is also -1. So basically from T to 2T will be the same value as this one. So unit wise they will be the same value. Numerically they will be the same value, but opposite sign. Okay, so that's what we need to remember. The rise over run is basically the same from T to 2T and 2T to 4T. However, alternatively, you could have done, to incorporate the minus sign, you could have done it like this also. This would have been also correct. The sign change and the constant regions that are important. Okay, a metal spring rests on a smooth table. The turns of the spring are equally spaced. The ends of the spring are now connected to DC power supply as shown. Spring is connected to DC power supply using flexible leads. The spring is not under tension. With reference to magnetic fields, describe and explain the change in distance between the turns of the spring when the power supply is first switched on. So when it's first switched on, there will be a magnetic field developed in the spring. So to understand this, remember, whenever we have two current carrying conductors, when the currents are in the same directions, the force between them will be attractive. Force will be attractive. And if the directions are opposite, force would be repulsive. So when the current flows through over here, so remember at a certain point, like right over here, the currents are in the same direction. So going, for example, if the blue ones are in the front, this one's on the back, so they're both flowing on the other side, they're in the same direction. So for example, if this is the front and this is the back, they're all flowing in the same direction. That's what we just need to explain. So when the power supply is first switched on, the current creates a magnetic field in the coil, and in the wire, in the wire at right angles to the wire, at every turn. So at the fields will interact with each other due to turns of the wire, since current flowing is in the same direction. Magnetic force between the turns will be attractive, causing the distance between them to decrease. Right, okay, so this is this question. Let's move on to the next one. Question number 7. A photon has an energy of 3.11 10 raised to the power minus 19 joules. Calculate the momentum of the photon. Okay, so how is momentum related to the energy? So we know energy is either hc over lambda, and h over lambda is the momentum. So if you want to find the momentum, that will be just energy over speed of light. So, right, okay. So we have energy 3.11 10 raised to the power minus 19. Speed of light is 3 10 raised to the power 8. So 3.11 divided by 3 times by 10 raised to the power minus 19 minus 8. 1.04 10 raised to the power, because 3 significant figures, 10 raised to the power minus 27. A laser beam has a power of 350 milliwatts. The light from the laser has a wavelength of 640 nanometers. Determine the number of photons emitted by the laser in a time of 1 second. Okay. So you see, power is energy over time. Energy, obviously, it's number of photons, so n times by a energy of 1 photon. Wait a second, is it the same thing? Energy divided by T. No, it's given a wavelength, so it can't be the same. So this is going to be n times by hc over lambda. hc over lambda. Right, okay. So we have 350 milliwatt equals to number of photons per unit time, basically. Actually, T should have been over here. And the energy of 1 photon is hc over lambda, 6.63 10 raised to the power minus 34. Speed of light 3 10 raised to the power 8. And lambda 640 nanometers. Okay. So, right, so 350 times by 640 times by 10 raised to the power minus 3 minus 9 divided by 6.63 divided by 3 divided by 10 raised to the power minus 34 plus 8. This is the value. Let's make it into standard form. So yeah, 1.1 10 raised to the power 80. Laser beam is incident normally on a surface that absorbs all the photons. Okay, show that the force exerted on the surface by the laser beam is given by this. Okay, so force is basically the rate of change of momentum, right? And so the change in momentum is hc over lambda divided by time. Oh, sorry, no. Okay, divided by time. So it is absorbing all photons. So, sorry, the n times by that. So we need it in terms of power. So we need it in terms of power. No, sorry, h over lambda. Okay. Actually, that was the what we could actually do about it. Right. Actually, that was what we could do about it. So if you multiply by c on numerator and denominator, this actually becomes the energy times by energy over t c, and E over T is power, so N times by E over T divided by C, and this is basically total power, and this is divided by C. Right, so that is the F is equal to P over C. Right, okay, moving on. Light of a single wavelength is incident on the surface of different metals. The work function energy of the metals is given in table 7.1. Okay, explain the term threshold wavelength. Now, we have this in the grade booster pack also, although this is frequently easy, but let's see that. Okay, so explain the term threshold wavelength. Threshold wavelength is the maximum wavelength of incident light that can cause photoelectric emission from a material. So, the maximum wavelength of incident electromagnetic radiation that can cause photoelectric emission from a surface. Okay, alright. For the metals in 7.1 table, calculate the value of the largest threshold wavelength. So we know that work function energy, phi, is hf or hc over lambda. So the one, if we need the largest, we need the lowest work function energy, potassium. So we will use the, and see, this is in the electron volt, so we need to convert it into joules. So lambda is hc over phi, 6.63 10 raised to power minus 34, 3 10 raised to power 8, 2.26, and 1 electron volt is 1.6 10 raised to power minus 19 joules. So this is something you need to remember always, times by 3 divided by 2.26 divided by 1.6 times by 10 raised to power minus 34 plus 8 plus 19. We get 5.5 10 raised to power minus 7. 5.50 10 raised to power minus 7. And that's it for this question. Let's move on to the next one. Question number 8. State what is meant by binding energy of a nucleus. So this definition is straightforward. This is also in the frequently examined questions. Is the energy required to completely separate the nucleons in a nucleus to infinity? That's it. So the energy required to completely separate all the nucleons in a nucleus to infinity. Right, okay. A nucleus of uranium-235 absorbs a neutron and becomes unstable. It then undergoes a fission reaction. One possible reaction is this. Determine the number of neutrons produced in this fission reaction. Okay. So as you can see, the number of neutrons will be the difference in the mass number. So 235 plus 1 minus 142 minus 90, 4. Easily. So 235 plus 1 minus 142 minus 90. Okay. Data for binding energies per nucleon for this fission reaction are given in the table 8.1. Calculate the energy released in mega electron volts from the fission of one nucleus of uranium-235. That means we need to consider multiplying for binding energies. We need to multiply 7.59 times by 235, 8.37 times by 142, and 8.72 times by 90. So 7.59 times by 235. Actually, we can do this one time already. So change in energy, or the energy released, would be the energy of the products. So 8.37 times by 142 plus 8.72 times by 90 minus 7.59 times by 235. So it will be 8.37 times by 142 plus 8.72 times by 90 minus 7.59 times by 235. So this is 189.69, which is roughly 190 mega electron. Okay, move on. The isotope xenon-142 is unstable. The isotope xenon-132 is stable. Okay. Suggest a reason why xenon-142 is stable. So it's due to the ratio between the neutrons and protons. When neutrons are higher than protons, the nuclei tend to become unstable. So one possible reason is that the neutrons, the number of neutrons in xenon-142 is greater than number of protons. Yeah. Okay. Xenon-142 decays into an isotope of cesium-142. Sample initially contains only nuclei of 142. After a time equal to 6 seconds, the ratio of decayed nuclei of 142 to undecayed nuclei of xenon-142 is equal to 31. Calculate the half-life of xenon-142. Show your working. Okay, so one mistake the students often make is that when we have this equation, minus lambda t, they think this is the number of decayed nuclei, but no, this is the number of undecayed nuclei. undecayed nuclei at time t, where n naught is like this is the number of starting undecayed nuclei. However, we have decayed nuclei also. So how do we reconcile these two information? So remember the exponential decay graph. Your xenon is starting like this. So this is your xenon. Let's call it xenon. Right. This is n, and this is your n naught. But your cesium is growing. And the number of cesium represents the number of decayed nuclei. So number of decayed nuclei, so they will become equal to that after at infinity, basically. Actually, it should be, let's say, like this. This is the number of decayed. The number of decayed nuclei is the number of cesium. Alright, so the number of decayed, as we can see already, this is the difference between number of starting nuclei n naught minus n, number of undecayed nuclei of xenon. Now in the ratio we are dividing this by number of undecayed nuclei, so when we divide this by n on both sides, this is equal to 31. N naught over n, and as you can see, 1, this becomes 1, and this goes on the other side to become 32. So when we take the ratio of n over n naught, this is 1 over 32. Okay, so this is how we reconcile these two informations. Okay, so now that we have n over n naught to be 1 over 32, now this is equal to e raised to power minus lambda 6 seconds. So we need to figure out what the lambda is. So we have ln minus ln 32, because ln 1 over 32 is minus ln 32, and this is equal to minus lambda 6. So lambda is equal to ln 32 over 6. Half-life, on the other hand, is just ln 2 over lambda. So ln 2 over ln 32 times by 6. So 6 ln 2 divided by ln 32, 1.2 seconds. Alright, so this is for this question. Let's move on to the next one. Question number 9. Electrons in a vacuum are accelerated through a potential difference of 84 kilovolt. The electrons then strike a metal target and X-rays are produced. Calculate the minimum wavelength of the X-rays that are produced. So minimum wavelength is when the entire kinetic energy of the moving electrons is converted into photon. So kinetic energy would be equal to the work done, QV basically. So QV equals to hc over lambda. So once we do that, hc over QV is 6.63 10 raised to power minus 34, 3 10 raised to power 8. Charge is 1.6 10 raised to power minus 19, and voltage is 84,000. So 6.63 times by 3 divided by 1.6 divided by 84,000 times by 10 raised to power minus 34 plus 8 plus 19. So this is 1.47, so we can rewrite it as 1.47 5. 10 raised to power minus 11. Okay. The melting point of two metals are given in table 9.1. Suggest why the metal target is made from tungsten rather than copper. Okay, so first off, we can already see that tungsten has a higher melting point, and not all the electrons' energies are converted into photons, X-ray photons. Some of its energy is lost into thermal energy at the target also. So, we can say that not all we can say that some proportion of kinetic energy of electrons is converted, not for like each electron, but some electrons are converted. Like instead of creating extra photons, they just simply lose their energy into the target. Some proportion of kinetic energy is converted into thermal energy at the target, causing heating effect. Therefore, tungsten would be a suitable choice as it has higher melting point. That's it. An X-ray beam is incident normally on a sample of soft tissue and bone. Data for two materials is given. Soft tissue, linear attenuation coefficient, specific acoustic. Total thickness of the soft tissue is X. Total thickness of the bone is also X. Incident intensity of X-ray beam is I naught. Transmitted intensity of X-ray beam is 13% of incident intensity. So determine X in centimeter. So it's also an exponential decay equation. So I equals to I naught e raised to the power minus mu t. Sorry, not t. This is thickness. The thickness, not time. This is t thickness. So okay. Basically, we have two things. We have soft tissue and we have bone. So the effect will be compounded. So the transmitted intensity from the, for example, the transmitted intensity from one of them will be the new I naught, and it will attenuate it differently. So the effect is basically compounded. So let's say for soft tissue times by E minus mu thickness t. So one is for the soft tissue, one is for bone. Okay, so I over I naught is 0.13 equals to minus mu per centimeter, so 0.22, thickness x minus 3x. So this is going to be 3.22 minus 3.22x. So now when we take the ln, this is going to be minus 3.22x. X would be ln 0.13 divided by minus 3.22. So ln 0.13 divided by, 3.22. So this is negative. So 0.63. Define the specific acoustic impedance of a medium. This definition, you can also find this in the grade booster pack, the frequently examined questions. However, this is easy. So this is the product of density of a medium and the speed of sound in that medium. Okay. Use the data from figure 9.2 to calculate the percentage of the intensity of ultrasound that is transmitted at a boundary between soft tissue and bone. So basically we need the reflected, and from reflected intensity we can figure out what the percentage transmitted is. So reflected intensity, let's call it IR. So you have divided by incident intensity, I naught. We know the ratio, that is Z1 minus Z2 whole squared divided by Z1 plus Z2 whole squared. So the graph is 1.7, 1.7, 7.8, 10 raised to the power 6. Okay. 7.8, 1.7, 10 raised to the power 6. No, sorry, 10 raised to the power 8. 6. And then you have 7.8 plus 1.7 squared, 10 raised to the power 6. Also squared. So obviously these two will get cancelled. So you are left with 7.8 minus 1.7 whole squared and 7.8 plus 1.7 whole squared. So this is this value. You subtract the 1 minus that. So this is going to be IR over I naught transmitted times by 100%. So we are getting 58.7, so basically 59%, you can say. Okay. The ultrasound is now incident on the sample of soft tissue and bone in figure 9.1. Suggests two reasons why transmitted intensity through the sample is less than the answer in C2. Okay, so the thing is, it's not just like soft tissue and then bone. This is not like this. There are reflections happening. There twice the reflection is happening. It's not just happening one time. The reflection is happening twice. More than one boundary. So reflections are happening more. So some obviously some ultrasound will be lost through attenuation also. So some ultrasound energy is lost due to attenuation through the tissues, through the soft tissue and the bones, and more number of boundaries are more, so more boundaries between soft tissue and bone mean more reflections, causing transmitted intensity to be lower. Alright, this was the second last question. Let's move on to the last question. Question number 10. Sun has a surface temperature of 5780 Kelvin. Luminosity of the Sun is this. Calculate the radius of the Sun. So basically we know the Stefan-Boltzmann law. L is equal to 4 pi r squared sigma t raised to power 4. So radius first square, luminosity 4 pi sigma t raised to power 4. Luminosity is 3.85 10 raised to power 26. 4 pi Kelvin 5780 raised to power 4, and Stefan-Boltzmann constant. Let's see the value. Okay, so this is the value, 5.67 10 raised to power minus 8. So 5.67 10 raised to power minus 8. So we have 3.85 divided by 4 pi divided by 5780 raised to power, raised to power 4 divided by 5.67 times by 10 raised to power 26 plus 8. Now we need to square root this value. We get 695,790,070. So we have 1, 2, 3, 4, 5, 6, 7, 8. So 6.95 three significant figures, so 6.95, 6.96, because you see 9, 5, 7, so 10 raised to power 8. Right. The Earth is at a distance of 1.5 10 raised to power 11 meters from the Sun. Calculate the radiant flux intensity F of the radiation from the Sun at a distance of this. Okay. So we know the radiant flux intensity formula, luminosity over 4 pi d squared. Luminosity is 3.85 10 raised to power 26 divided by 4 pi. Distance is 1.5 10 raised to power 11 squared. 3.85 divided by 4 pi divided by 1.5 squared times by 10 raised to power 26 minus 22 is 136. 1300, sorry, we can say 1360. Unit would be watt per meter squared. Right, okay. The variation with wavelength of the intensity of the radiation emitted from the sun is shown. Okay, another star has the same radius as the sun but has a lower surface temperature. On figure 10.1, sketch a line to show the variation with wavelength of the intensity of the radiation emitted for this star. So it will be slightly lower and peak would be like this. So, like this. Actually, sorry, no. The second part, not so much. It might be basically like this. Okay. So basically, lower surface temperature would mean that the wavelength would be higher, and since we know the Wien's displacement law, lambda max inversely proportional to temperature, so lower. That would also mean lower intensity also. Okay, all right. The galaxy in constellation Corona Borealis is moving away from Earth. The visible emission spectrum for the Sun is shown in figure 10.2. The lines are at wavelengths 397, 410, 434, 486, and 656 nanometers. The compositions of the Sun and a star in Corona Borealis galaxy are similar. On figure 10.3, sketch the emission spectrum for the star in Corona Borealis galaxy as observed from the Earth. No calculations are required. So basically all the wavelengths would be slightly towards longer wavelengths. Also, one thing to notice over here, although like slightly longer, so even if you pull them like this, longer like this, and maybe somewhere closer to 500, and 650 somewhere like this. This would be sufficient. However, you have to remember that the difference in lambda, if for example they are same, so this would be proportional to the lambda itself. The lambda is the lambda of the lab one. So the redshift, basically, this is the, let's say the redshift. So redshift is the same like V over C over here. So the difference in wavelength would increase with the wavelength. So higher the wavelength, more the difference apparent over here. So longer wavelengths, right? Actually this one would be slightly closer. Slightly closer to this, and right, okay. The galaxy in the Corona Borealis is moving away from the Earth at a speed of 21,400 kilometers per second. Use the information for B1 to calculate in nanometer the observed wavelength of the lowest visible energy spectrum, lowest visible energy emission. So we know that the lowest visible energy emission, basically this would be inversely proportional to the wavelength. The lowest energy would mean the highest wavelength. So that was the 656, right? So that's what we will do over here. So observed wavelength minus the 656 nanometer divided by 656 nanometer equals to speed 21,400 10 raised to power 3 to convert it into meters, and 3 10 raised to power 8. So you have 2 1 4 10 raised to power, basically like divided by 300. You see, basically this would become 10 raised to power 5. And you can also write it as, actually no, 3000. 1, 2, 3, 10 raised to power 5. So 3000, my bad. So this times by 656 plus 656 will get you this value. So observed wavelength would be 702.79, so 703. The wavelength in B2 is used to calculate a value for the surface temperature of the star in Corona Borealis. The calculation does not give an accurate value. State and explain whether this value of the temperature is too high or too low. So because the wavelength is high, the observed temperature, calculated temperature, would be lower. So the wavelength observed is higher due to redshift. Hence, the calculated temperature would be lower. Than actual value. Right, and that's it for question number 10 also, and that would be the end of this paper. I hope you enjoyed the explanations that we gave. If you have any questions, confusions, or doubts, feel free to reach out in the comments. If you would like us to do any specific paper also please reach out in the comments. I would love to help you. Do check out the Grade Booster Pack on Patreon. The link is below in the description also, and then you can see in the video also. And if you like this video, give it a thumbs up, subscribe to our channel, and turn on the notifications for future updates. Meanwhile, see you in the next video. Bye bye.